Welcome back, AP Bio, to Chapter 2.5, where we're going to be talking all about water and pH. So, water is one of the most important substances for life. The majority of any living creature is made up of water. Biology, when we really look at it from a simplistic view, is a solution based science: what mixes with what and how that's changing. And water is also really cool because it's one of the few substances on Earth that can exist in all three phases, that's solid, liquid, and gas, under normal conditions on the planet. So let's dive into some of these properties that makes water so cool. To start off, we have molecular polarity. So some atoms have a stronger electronegativity, or that attraction to electrons, than others. As a result, in covalent bonds, sometimes electrons can be unevenly shared between those atoms. So, for example, in a water molecule, because oxygen has a stronger electronegativity than hydrogen, even though they're sharing electrons, those electrons are going to be closer to oxygen than they are hydrogen. This is going to result in those atoms with that more dominant share of electrons being slightly more negative and the other atoms being slightly more positive. Now, depending on the shape of the molecule, if it has poles or opposite ends, like this water molecule, where one side is negative and the other side is positive, you end up with a polar molecule. So let's look at some examples of this. When a molecule like water has those different partial positive and partial negative sides, we can see that it's polar. Whereas something like carbon dioxide, because you're going to have in opposite ends with the positive and negative sides, or like methane, you're going to end up with a non-polar because there's not one side that's positive, another side that's negative. This allows for water to be a really great solvent. Now, water is sometimes referred to as the universal solvent. Technically, there's no such thing as a universal solvent, but water is really close. And that's because of that polarity. So, opposite poles in water are going to help disassociate molecules into ions. And then the positive and negative sides are going to be attracted to those positive and negative ions, and they're going to form a hydration shell around either polar molecules or ions, and this is going to prevent them from rebonding and kind of surround them with a protective sphere of water, or a hydration shell. So it's important to just remember some basics of solutions, since we're talking about a solution-based science here. A solution is a mixture in which a solute, or what's dissolved in the solvent, is evenly distributed. So when we dissolve salt into water, it creates salt water because that salt gets dissociated. The sodium and chloride ions get dissociated and protected by those hydration shells. This is important because dissolved substances can move in and out of cells a lot more easily. And we'll talk about that more when we get to membranes. So another big important thing that polarity allows for is something called hydrogen bonding. Now, hydrogen bonding is not a true bond. It's really just a strong attractive force. And so this is where opposite charges on either pole of a water molecule is going to be attracted to those other polar molecules. So you can see like positive hydrogen is attracted to negative oxygen, and that's going to hold them close together. Hydrogen bonds come up a lot in biology. One example is your two strands of a DNA molecule are held together by hydrogen bonds. So, one thing that hydrogen bonding allows for is something that has really allowed for there to be so much life on planet Earth, and that's that ice floats. Now, it seems normal to us because ice has always floated, but this is really, really cool. Most of the time, something that's solid is going to be more dense than something that's liquid, and so it sinks. However, because of those hydrogen bonds forcing solid water into that crystal lattice structure that you can see here, and it creates this even spacing all throughout the structure, it's going to actually be less dense than water, which, because it has a little more energy, can break those hydrogen bonds and becomes a little bit more dense as those molecules are sliding against one another. So floating ice is so important because it's going to insulate water below it instead of all of the water freezing. And this is going to allow for constant winter temperatures under the ice and allow for life to thrive. If ice sank, it would just continue to freeze all the way to the top. Another cool feature as a result of all of these hydrogen bonds is that water has a really high specific heat and heat capacity. So, what is that? Well, water can absorb a lot more energy before you start to see an increase or decrease in temperature because those hydrogen bonds are holding those atoms together so they don't start moving more rapidly as a result of heat as quickly. And so temperature doesn't go up. So you can see like the difference there between water and iron and their specific heat. Water is way higher than iron, nearly 10 times as much. And so that's why when you put a pot on the stove, the water in the pot stays cold for a while the pot heats up right away. Also, because of water absorbing heat, it helps us cool down. So, like we sweat, that's going to draw heat away from our bodies to help us cool down. But water not only absorbs heat, it retains heat really well. So that's why coastal regions are usually cooler than hotter surrounding areas, or coastal regions may stay warmer than surrounding cold areas. And so it helps regulate biomes near water bodies. Another cool thing about these polarity and hydrogen bonding is things like cohesion, where water molecules will stick together, and adhesion, where water molecules will stick to other polar objects. So, cohesion, working together. Adhesion is where they're sticking to other polar objects. Water has both of these abilities and it allows for a lot of really cool things. So, for example, cohesion, molecules sticking together, allows for high surface tension. So, like this little spider can be walking on water because it doesn't have the weight to break through the hydrogen bonding on the surface. Adhesion allows for transpiration, or the movement of water up to the very top of a tree. So, also very important for life on Earth. One of the last things that we're going to talk about with water is pH. So, pH is probably something you've tested in the past, and it's a measure of how acidic or basic a solution is. And you've probably seen this pH scale going from 0 to 14, 0 being extremely acidic, 14 being extremely basic, and 7 being neutral. But what does this really mean? What is an acid? What is a base? What is pH? So, because water is so polar, water can actually break itself apart. And this is going to produce hydronium ions, which are hydrogen ions. Also, you could represent it as H3O because it's water plus a hydrogen ion. Or hydroxide ions, which are OH ions, which are going to be negative. So, in pure water, the concentration of these ions is going to be equal. So, positive, negative, and that's going to give us a rating of 7. But because we're measuring these hydrogen ions here, these hydronium ions, pH actually is going to stand for power of hydrogen. That's what the P and the H stand for. And it's a logarithmic scale based on the concentration of these ions. So because acids are going to donate protons, they are going to have more hydronium or H3O or more hydrogen ions than OH ions. And bases are accepting protons or ripping protons off of things because they have that negative charge, since they have more hydroxide ions than those hydronium or hydrogen ions. So if you've ever wondered what acids and bases are doing, there you go. One last thing, there's something called a buffer. And buffers are really important for biology. Life requires a really stable and narrow pH. For example, your blood has a pH of around 7.4. And if your blood pH varies by over 0.4 on that pH scale, you're going to die because you're just not able to cope with that toxic environment. Think about our oceans when we talk about ocean acidification. Oceans aren't changing wildly. But because life requires such narrow ranges for success, you start to see these coral reefs dying and bleaching, and because that pH is changing slightly, and it's preventing calcifiers from being able to form shells, and all sorts of things are going on. So luckily, we have buffers, which are compounds that react chemically with acids and bases in order to neutralize the effects of those ions. So for example, if we had water and added an acid, its pH would drop precipitously. But with a buffer, it's a much more stable descent. And so we have buffers in our systems to prevent wild swings in pH. Well, that's it for chapter 2.5. See you next time.